Okay, so in this lesson, we're going to talk about some simple and common ways to visualize conditional probability and joint probability. And in doing so, I'm going to kind of help you get used to keeping these related things distinct. Okay, so just to recap, when I say joint probability, that's the probability of the intersection, but as we're kind of moving away from set theory and moving more towards random variables, I'm going to start using slightly different lingo, and joint probability is where we're going with that. So the joint probability, that is the probability of the intersection. Okay. It's the probability that both E and F happen, and it indicates that we're uncertain about both of them. Okay, that both of these things are still random, they're unknown, we can't pin them down. Okay, conditional probability means that we've learned one of the two things. Okay, so probability of E conditional on F means that F is no longer random. It's no longer uncertain. We know that F is real. The only remaining uncertainty is about E, and we might want to change the probabilities associated with that uncertainty to reflect the fact that F has happened instead of something else that could have happened. Okay. Sometimes we get information in terms of conditional probability, and we want to do is calculate joint probabilities. And sometimes we get information in terms of joint probabilities, and we want to calculate conditional probabilities or total probabilities. So you want to be able to move fluidly back and forth between the two things. So I'm going to talk about two kinds of diagrams to use. First, trees, which are most helpful when we're getting information in terms of conditional probabilities. I'll do an example of that. The other is crosstabs, which is just a tabular format, which is most useful when we're getting information in terms of joint probabilities. Okay, so just summarizing that. Use trees to go from conditional to joint. Okay, somebody gives us, or we assume the natural way to think about things are in terms of conditional probabilities, and when we get to joint probabilities, the tree will help us with that. But if we're given the joint probabilities, or again, that's our natural starting place, use crosstabs. Okay, so let's first do an example where we're given information in terms of conditional probability. And as I go through this example, I think you'll recognize this happens like all the time here. So this example is going to be about ideology. And we're going to be thinking about there being sort of two aspects to ideology. You can be economically liberal or conservative, and you could be either socially progressive or socially traditional. Okay, so those kind of two dimensions of ideology appear in a lot of contexts that can help us understand a lot of shared belief systems. So in our example here, say we've got a group where the probability of being liberal is 0.4. Okay, if you're not liberal, you're conservative. Okay, so the complement of liberal is conservative, and what that means, I'm going to switch color here. Erase for a second. Switching color here because if I say that the probability of being liberal is 0.4, and if you're not liberal, you're conservative, then we know, so the stuff in red is things that we're inferring here, is the probability of being conservative is 0.6. Okay. So another thing that we might be told is that the probability of being socially traditional, Okay, so being conservative on the social as opposed to the economic dimension, given that you're economically liberal, is 0.2. Okay. And the complement of traditional is progressive. So again, we know something that is true now just in the world of a person being liberal. But this and this together imply that the probability of being progressive, conditional on being liberal, is 1 minus the probability of being traditional. Okay. But the probability of being traditional, conditional, and being liberal doesn't tell me anything about the probability of traditional, given that you're conservative. Okay, so the within conditioning event, holding what's after the bar constant, our probabilities have to sum to 1. But now when we're going to change the world we're in, now we're in the world of an economic conservative, there's no restriction there. What's going on in the model of what happens in the liberal world doesn't affect the, at least probabilities don't affect what's going on in the conservative world. What we think about politics and the way the world works, that will affect both of these things. So if we assume that the probability of being socially traditional, given that you're economically conservative, is 0.7, same story here. Opposite of traditional is progressive. And so again, we're required to say that the probability of being progressive, traditional on being economically conservative is 1 minus that 0.7, so 0.3. Okay. So that's a set of assumptions. This would be a probability model here. This is what we're given. Actually, what we're given is in blue. What the Kolmogorov axioms require is in red. And now we want to organize this information to calculate the joint probabilities. And we're going to do that with a tree. So I'm just going to do a tree. Because the first node is going to be, is the person liberal or conservative here? Okay, and so on this node, probability of being liberal is 0.4, and the probability of being conservative is 0.6. Okay, so we go down this liberal path here, and so we know the person is liberal. The next node here tells us, well, is this person traditional, given that they're liberal, or are they progressive, given that they're liberal? And we have those numbers given to us as well. So I'm putting on the branches of this tree, I'm putting the probabilities associated with the node. So probability of being traditional, given that you're liberal, is 0.2. The probability of being progressive, given that you're liberal, is 0.8. Down here, given that you're conservative, the probability of being traditional, given that you're conservative, we said that was 0.7, and the probability of being progressive, socially progressive, given that you're economically conservative, is, where did that one go? That's 0.3. Okay. What I've now got in the tree is everything. So all I've done is just taken these numbers and I'm organized them into a tree. But the tree structure is nice because now if we want to calculate the joint probabilities, we've got kind of paths leading to each of the joint probabilities. You're liberal and you're traditional. What we get to at the end here is the person being the probability of the person being liberal and traditional is indeed the product of the probabilities on all the branches. Okay, so to get that number, it's just 0.4, 0.4 times 0.8, 0.32. And the probability that I am liberal and progressive. That's down here. So I've gone down the liberal path and then the progressive path there. And the probability, joint probability, is the product of being liberal and then being progressive, conditional on liberal. So 0.4 times 0.8. I think I wrote some bad numbers up here. Okay. 0.4 times 0.8, that is 0.32. Let's go back and look at what I wrote here. This is the probability of being liberal, but this is not the probability of being traditional, conditional on being liberal. That should be a 0.2. Okay, so that needs fixing. Let's fix it. Probability of being liberal and traditional is probability of being liberal, and then traditional conditional on liberal is 0.2, and that is 0.08. Looks good so far. Let's see how I do in the other branch of the tree. Joint probability of being economically conservative and socially traditional. Again, I'm going to take the probabilities on the branches and multiply them. Okay, so 0.6 probability of being conservative multiplied by a 0.7 probability of being traditional given that you are conservative. That works out to 0.42. And the final joint probability is the probability of being economically conservative and socially progressive. That is 0.6 times 0.3. That equals 0.18. Okay, so that's what you can do with trees. You can calculate joint probabilities that way. You don't need a tree to do it, but a nice thing about the tree is often, well, two things about it. It puts all of the information in the model in one diagram you can look at. And by putting it all in one diagram, it helps you check that everything is adding up correctly. Also, by having it all in one diagram, you can kind of make lots of calculations based on one little picture. So things to check to make sure that your tree diagram is correct is with anytime you're working with probabilities, anytime you're putting them into a diagram, you always want to be asking yourself, okay, what's supposed to add up to 1? What doesn't matter? So some things that have to add up to 1 in a tree is, first of all of these end nodes, the ones that represent the joint probabilities, all 4 of them in this case, or however many we had, given how big the tree would be, these must sum to 1. Okay, so that's one place where these must all sum to 1, and 0.08 and 0.32 is 0.4, 0.82, it does sum to 1. The other place where things have to sum to 1 is at each node branch probabilities must sum to 1. Okay, so at each node, 4 and 0.6 have to sum to 1. 0.2 and 0.8 have to sum to 1. 0.7 and 0.3 have to sum to 1. Okay, so trees are cool. They're a good way for organizing information that comes to this in this kind of, oh, we split the group in 2, and then within each group, here's what's going on. It's a very natural way that we convey information, is in this conditional sense, and the trees can help us organize that. Sometimes, though, we're given the joint probabilities. So let's just say we started with these numbers here, but we didn't know any of the other stuff. All we were given is the joint probabilities. Then the natural way to display those would be in terms of a crosstab. So that's just a 2x2 table. I'll put liberal and conservative on the rows, and progressive and traditional on the columns here, and just remembering the numbers. So I'm assuming that these green numbers are what we're given here, that this is 0.32, 0.08, 0.18 and 0.42. Okay, so we just got that number. Here's a group, and 32% of them are liberal and progressive, 8% of them are liberal and traditional, 18% are conservative and progressive, and 42% are conservative and traditional. That's just another way that this kind of information could be conveyed. This would be a natural way to depict it. And often what we do when we set things up this way is we calculate what's called marginals. Okay, so what we do is we add across the rows and we add across the columns to get the probabilities of bigger events. So adding the probability of being liberal and progressive and the probability of being liberal and traditional. Oh, look, that's a partition of being liberal, right? Because P and T are complements. So these this is a mutually exclusive and exhaustive way of writing L in terms of subsets there. Okay, that part's cool. Because they're mutually exclusive, it also means that we can calculate the probability of the union just by being by adding up there. So that is probability of being liberal, and that is 0.4, which is what we started with. That's good. Okay, if we didn't know that, we could get back the information that we started with. It should be conditional, should be consistent with this. And similarly, adding across this row, the probability of being conservative. Well, there's two ways to be conservative. You can either be conservative and socially progressive or conservative and socially traditional. We add these up, 0.18 plus 0.42. And we get 0.6. We can also add down the columns to get the probability of being progressive. Two ways to be progressive. We can be progressive and liberal or progressive and conservative. Adding those up, 32 and 18 is 0.5. And the probability of being traditional, again, we add up, probability of being traditional and liberal, and being traditional and conservative, that is 0.5. Okay, so these broader probabilities, you might call them total probabilities, what people do call them is marginals, because we write the probabilities in the margin. Okay. And then once you have the marginals, if you want to calculate the conditional probabilities, you've got all the information that you need for that. So if we wanted something like, what is the probability of being liberal, if we know that you're socially progressive, well, it's, remember the definition there, the probability of being both those things divided by the probability of the conditioning event. And we have that. We have the probability of being liberal and progressive, that's right here, 0.32. And we also have the probability of just being progressive, that's our marginal here, 0.5, 5.5, and that is 0.64. As always, when we have unconditional probability and a conditional probability of the same event, it's never a bad idea to ask yourself, does it make sense? Does it make sense that if we know somebody is socially progressive, that makes us think the probability they're economically liberal is higher than it was before we knew that? Yeah, it makes sense, okay? It makes sense in this model precisely because the liberal people are economically liberal are more likely to be socially progressive. So we can use the crosstab to calculate marginal probabilities and use those to get conditional probabilities if we need it. Okay. The thing that we can't do, and this is something I was kind of emphasizing at the end of the last lesson too, let's say that we just started, I'm going to go to a new page, so I'll just highlight the numbers that I'm going to bring over. Let's say that we just knew the marginals. Okay, we didn't know the conditional probabilities or the joint probabilities. Okay, suppose we just start with the probability of being progressive is 0.5 and the probability of being liberal is 0.4. Here's the thing that please, if you've had Poli-Sci 200A, please never do this. You cannot calculate the probability of being progressive and liberal by just multiplying these probabilities together, because they're not independent. And it would be, anybody who knows anything about politics would not assume that these things are independent, right? Okay, so this does not equal the product of being progressive and liberal. What would we get for that probability? Well, we would get 0.2, okay? And where did these numbers come from? No, they came from a much higher probability here, okay? This does not equal, okay, does not equal here. So let's just emphasize that when we multiply the marginals, we get 0.2. That doesn't mean anything. That is just a number that's not remotely useful in this model, because the true probability, the true because I made up the world so I get to say what's true here, of being progressive and liberal was 0.32. Okay, cannot multiply marginals to get joint because P and L are not independent. Okay, great. So this ability to work with conditional and joint probabilities lets you do a lot of kind of applied probability modeling. So you're ready to go for it.